Hello, everyone. I'm Mohammad Roghani. I'm going to talk about sublinear time algorithm for Steiner tree via improved bound for set cover. This is a joint work with Sepida Mahabadi and Jakub Tarnowski from Microsoft Research, and also Ali Vakilian from TTIC. This work has been done while I was intern at Microsoft Research. So first, I'm going to define the Steiner tree problem. So the input of the Steiner tree problem is a weighted graph G with n vertices and set of k terminals. So here is an example of the input graph, and the set of blue vertices are the terminals, and black vertices are the non-terminals vertices. And we can also assume that we have access to a metric that is produced by the shortest path distance in G. So we can query what's the shortest path between, we have access to distance between every two vertices. And the output, the goal is to find the subgraph with minimum cost that connects all the terminals. So for example, in this given graph, the set of red edges is the minimum cost connected subgraph that connects all the blue vertices, which are the terminals. This problem has been extensively studied in the literature. It was proven by Chlebik and Bikova in 2008 that this problem is approximate hard with the factor of 96/95. And also, the best known approximation algorithm for this problem in the polynomial time is log of 4 plus epsilon, which was the result of 3 different papers. Also, I'm going to define what is sublinear time algorithm and motivate the reason that people study this study this setting. So the motivation is the big data. We have access to a large data set that is so massive that we are not even allowed to read the whole input. It's so big that spending time to read the input is not sufficient. So for example, you can consider the graph of social network. People in this graph are nodes, and two person are connected if they know each other. So such a network has billions of nodes and also even more edges. So linear time algorithm with respect to the size of the input, which is the number of the edges here, are not sufficient. So the goal is to design algorithm that produce the output in sublinear time with respect to the size of the input. So the metric Steiner tree problem in the sublinear model, again, we are given n vertices and k terminals. And the goal is to find the minimum weight subset of the edges that connects all the terminal vertices. And we have access, we can query the distance between two vertices. So here the number of, also we assume that the metric, the adjacency, the distance matrix is metric, so it satisfies the triangle inequality. So here, because the distance matrix has n squared elements, so because we are thinking about the sublinear model, we want to design an algorithm that works in subquadratic time. And also we want to minimize the approximation ratio, and we want to get closer and closer to the optimal solution. And so for many of the problems in the sublinear model, it's hard to find the actual solution. So for example, consider different problems such as metric minimum spanning tree, metric traveling salesman problem, maximum matching hierarchical clustering, and many more problems. It's hard to output the whole instance. For example, for the maximum matching, it's not possible to output any approximate maximum matching, edges of the approximate maximum matching, but it's possible to estimate the cost of the solution. For example, you can estimate the size of the maximum matching with some constant approximation factor, but you cannot output the edges of the maximum matching. This is also the case for the metric Steiner tree problem. So we look for a more relaxed question, that what is the cost of the Steiner tree problem, and not what are the edges of the Steiner tree. I'm going to briefly talk about the prior works. So Gilbert and Pollock in 68, they proved that if we find the MSC cost over the metric induced by the terminals, this is a two approximation for the metric Steiner tree. And Shumaj and Sohler in 2009, they proved that it's possible to estimate the cost of the MSD with factor of 1 plus epsilon in order of n time. So this will immediately result in two approximation algorithm for a Steiner tree problem in order of n time. Chen, Hana, and Tan very recently, they proved that it's possible to break this two approximation barrier, and they give a slightly better than two approximation for the Steiner tree problem in N2 13/7 time. So we can ask this type of question, that what is the query complexity of this Steiner tree problem if we want better than two approximate solution? So can we push it all the way, for example, to the order of n time? Chen, Hana, Tan, in the same paper, they proved that better than two approximation for Steiner tree problem requires omega of n to 6/5 time. So now we can ask, is the algorithm by Chen et al. Tight? So does the problem require n to 13/7 time to get better than two approximation? We answered this question. We made a progress for this question. We proved that if we want to, there exists an algorithm that with approximation that better than two approximation factor, that estimate the cost of the Steiner tree in order of n to 5/3. So now I'm going to define another problem, which is called threshold set cover problem, which we reduce the Steiner tree problem to this new threshold set cover problem. So consider this example. Suppose that the input metric only contains edges of weight 1 and 2. And we first start by finding an MSD of the metric induced on the terminals. So here in this given graph, so the MSD of the terminals, which are the blue vertices, are this path of edges with weight 2. And we know that, as we mentioned previously, up to this point, when we find the MSC of the induced metric on the terminals, we have to approximate solution. So all we need is to just find local evidence to show that we can improve the solution using non-terminal vertices. So if, for example, in this graph, if we remove two of edges of weight 2 and replace it with the 3 red edges of weight 1, we reduce the cost of the Steiner tree by 1. So these local evidence are enough for us to show that we can actually get better than two approximations. So all we need is to find these local evidences. So in the threshold set cover problem, which was defined by Chen, Hana, and Tan, they prove that there is a reduction to an instance of set cover problem that we call it threshold set cover. So we have a set of we have different sets, and also we have elements. So here elements are corresponding to our terminals, and non-terminals are the sets. So we want to cover these elements using non-terminals to decrease the cost of the Steiner tree. So we are given a universe of elements U and a collection of sets F. And we have access to membership oracle of our instance, so we can query if if one element is inside one set. And the goal is to estimate the size of the universe minus the set cover solution of the instance. So if this value is large, it means that we can save on the solution costs of the Steiner tree problem, which means that, for example, you can use one non-terminal to connect all those terminals and decrease the cost of the Steiner tree by a lot. So what we are actually interested in is to estimate the size of the universe minus the set cover solution. And also we allowed to have some epsilon and additive error. And we want some constant approximation for this problem to just fit to approximation in the Steiner tree problem. So Chen, Hana, and Tan, they proved that there exists an algorithm that estimates the cost of threshold set cover problem in N2 7 over 4 time up to a 1/4 multiplicative and epsilon and additive factor. In this work, we proved that it's possible to estimate the cost of threshold set cover in N2 5/3 time up to 1/4 and epsilon and multiplicative additive factor. So, and this subroutine that was used in the previous result can be a speed up and then result in the faster algorithm for a Steiner tree problem. So next, I'm going to talk about the techniques, overview of the techniques that used to use for solving this threshold set cover problem. So the first part of our algorithm is the sparsification of elements and sets. I'm going to describe each of them one by one. So for the elements, again, so, we have n sets and we have k elements. And suppose that x is some parameter that we are going to optimize later, is something between 0 and 1. So assume that we sample n to 1 minus x sets and add them to the solution. So we can add these many sets to the solution because it's smaller than epsilon n, x is larger than 0. So we can cover it using the additive error that we are allowed to in the approximation factor. So now consider an element that appears in more than in omega of n to x sets. For such an element, we expect to have a large intersection with the chosen sets, with the sampled sets. So we can remove the elements with large degrees. So because we know that all of them are going to be covered using this n to 1 minus x sets that we sampled. And also we know that for each of these sampled sets, we need to query all the elements. So the total time is going to be n to 2 minus x. So by spending n to 2 minus x time, we are able to remove all the elements that have degree larger than n to x. So this assumption that elements degree is at most n to x is without loss of generality if we spend n to 2 minus x time. We can also sparsify the set size, sparsify the sets. So suppose that we iterate over the sets one by one, and for each of them we sample n to 1 minus x remaining elements in the universe, uniformly at random. So if there is a large intersection between the sampled elements and the sets that we are iterating over, we add the set to the solution and remove the set and its elements from its elements. So if a set contains more than n to omega of n to x elements, it means that we are going to have a large intersection. And since each removed set is going to contains at least omega of n to x element, this even happens at most of order of n to 1 minus x time, that we can afford to have it using the additive error in our estimation. So therefore, again, by spending n to 2 minus x time, we can remove all the sets with degree larger than n to x. So now we construct a graph called H. It's an auxiliary graph that we use for that we use as a proxy to solve our problem. So suppose that the vertices of this graph H are the elements, and two vertices are connected if their corresponding elements appear in a set together. For example, in this instance that we have 4 sets and 6 different elements, the graph contains 6 vertices, and 2 vertices are connected if they appear in the same set at least once. So here you can see that the set of black edges are corresponding to set S1, the set of blue edges are corresponding to set S4, the set of red edges correspond to set S2, and the set of green edges correspond to set S3. So we can prove that if the set cover of the instance is small, then the maximum matching of H is going to be large. For example, suppose that there exists one set that covers all elements. So it means that the graph is a clique, so and we have a large maximum matching. If the set cover is large, for example, we need, if we have k elements, we need like k sets to cover all of them. It means that there exists no edge in the graph, for example, in this extreme case, and the maximum matching is 0. So if the set cover is large, set cover solution is large, the maximum matching is going to be very small. So therefore, we can use the size of the approximate matching to estimate the size of the threshold set cover problem. And we have a rich toolkit for approximate maximum matching in the sublinear setting that we can use to solve this problem. So for the sublinear matching, suppose that D be the average degree of the graph. There exists a result by Behrajat that proved that there exists an algorithm that estimates the size of the maximum matching of the graph up to a half multiplicative factor in order of the average degree, given access to the adjacency list of the graph. So here, in our application, the average degree of the graph is n to 2x. The reason is that each element is in at most n to x sets. Also, each set has at most n to x elements. So 2 elements appear in the same set in the same set. So each element is appeared with at most like n to 2x other elements. So also finding the adjacency list of a vertex cost n to 1 plus x. That's because for each element we can query all the sets that it contains. It's going to be n to x, and for each of them we can query all their elements, which costs at most n to 1 plus x. And we know from previous slides that a sparsification cost is going to be n to 2 minus x. And so the total cost is going to be n to, if you write down all these like constraint that we have and optimize for x equal to 1/4, we get order of n to 7/4. So that's exactly the result of the Chen et al. Paper with some modification. That's not the exact algorithm, but that's with some modification. This is going to be a very simplified version that you can get n to 7/4. So, but one observation that will help us to speed up this algorithm is that the matching algorithm doesn't need the entire adjacency list to work in the exploration step. At each of the exploration step, the algorithm needs only a new random neighbor of the given vertex. So, for example, suppose that V is an element with degree D in auxiliary graph H. We first query all sets to find the sets S that in family of sets that include V. We call those family of sets S. We know that the size of S is at most n to x because of the sparsification step that we had. Now we start to randomly query pairs of elements and a set in S. So we know that because the average degree of V in H is D, because the degree of V in H is D, we expect to find a random neighbor of V after spending n to 1 plus x over D queries. N to 1 plus x is all possible pairs, and we know that D of them are edges. So after n to 1 plus x over D queries, we expect to see one of those edges. So the total cost for seeing a random neighbor is order of n plus n to 1 plus x over d, and the first n in the total cost of seeing a random neighbor appears for the first step that we query all the sets to find the sets that include v. So also there are other technical challenges. For example, a neighbor of an element in H may appear in many sets. So to overcome this challenge, we'll let H to be a multigraph instead of a graph that's two vertices can have multi-edges because of different sets that they appear together. And we prove that the matching algorithm also works on the multigraphs with the same running time. And the other challenge is that the vertices with degree far from, so what we proved in the previous slide for the cost that we see a random neighbor was for average degree, for vertex with average degree, but vertices can have different degrees. We proved that the number of times that the matching algorithm visits a vertex in its exploration step is proportional with its degree, and that two terms that depends on degree will cancel out. And finally, we can put everything together. So we know that the sparsification cost is n to 2 minus x. We know that the exploration size of the matching algorithm is the average degree of h, which is n to 2x. And the cost of finding a random neighbor is n plus n to 1 plus x over d. So the total cost, if we consider all these steps, is going to be n to 2 minus x plus n to 1 plus 2x, which we can optimize by setting x equal to 1/3. So the total cost will be order of n to 5 over 3. So we can now mention our result one more time, that we can estimate the costs of threshold set cover up to 1/4 multiplicative and epsilon and additive factor in order of n to 5 over 3. And that's enough to solve the cost estimation of the Steiner tree problem for approximation better than 2 in n to 5 over 3 time. And there are some open questions. For example, maybe the interesting one is, can we get better approximation? By better approximation, I mean beating 2 by a large constant in sublinear time. The current approximation is just slightly better than 2 approximation for a very small constant. So it's interesting to see if we can beat 2 by a large constant. For example, can we get 1.9 approximation in sublinear time? And the other open question, which is more general, is to come up with sublinear time algorithm for other metric problems. For example, traveling salesman problem. For traveling salesman problem, again, using the metric MST estimation, you can get 2 approximation, but beating 2 approximation is the longest standing open problem. Thanks for listening to this talk.